Hi, my name is Brian Caffo and welcome to the lecture on some common distributions in the Statistical Inference Coursera class as part of our data science specialization. The specialization is co-taught with my co-instructors Jeff Leake and Roger Peng. We're all at Johns Hopkins University in the Department of Biostatistics in the Bloomberg School of Public Health. Let's start with perhaps the simplest distribution, the Bernoulli distribution. The Bernoulli distribution is named after Jacob Bernoulli, a famous mathematician who actually comes from a family of famous mathematicians, and if you're interested you can read up on the Bernoullis. They have lots of Wikipedia pages, for example. So the Bernoulli distribution arises out of a coin flip, say with a 0 for a tail and a 1 for a head. And you have a potentially biased coin with probabilities p for a head and 1 minus p for a tail. We usually write the Bernoulli probability mass function as p to the x 1 minus p to the 1 minus x. The mean of a Bernoulli random variable is p, and the variance is p times 1 minus p. We've seen these facts before. And if we let x be a Bernoulli random variable, we typically call x equal 1 as a success, regardless of whether or not the outcome is successful in some sense of the word, and x equal to 0 as a failure. Now that we've discussed the Bernoulli distribution, let's talk about the binomial distribution. A binomial random variable is obtained as the sum of a bunch of IID Bernoulli random variables. So ostensibly, a binomial random variable is the total number of heads on the flips of a potentially biased coin. Mathematically, let's let x1 to xn be Bernoulli p, then x, the sum of them, is a binomial random variable. The binomial mass function looks a lot like the Bernoulli mass function, though with n choose x out front. Recall that the notation n choose x stands for n factorial over x factorial n minus x factorial, and n choose 0 and n choose n are both 1. This solves a particular combinatorial problem of counting the number of ways of selecting x items out of n without replacement, disregarding the ordering of the items. Let's go through a quick example of a binomial calculation. Suppose you have a friend who has 8 children, 7 of which are girls and none are twins. If each gender has an independent 50% probability for each birth, what's the probability of getting 7 or more girls out of 8 births? Well, let's plug right into the binomial formula. That's the probability of 7, which is 8 choose 7, 0.5 to the 7, 1 minus 0.5 to the 1, plus 8 choose 8, 0.5 to the 8, 1 minus 0.5 to the 0, which works out to be about a 4% chance. Here I give you the R code for performing this calculation. Also, as with most of the common distributions, there's an R function, and p binom gives you these probabilities.